So these are your notes over periodic trends. So go ahead and write these down, pause the video, and write these down as we go. Okay, so the three main periodic trends we're going to be talking about are three that you've actually already looked at a little bit in the it's in the cards activity that you should have finished up. Atomic radius, ionization energy, and electronegativity. So let's look at atomic radius first. So there's your definition. Atomic radius is half the distance between the nuclei of identical bonded atoms. The reason that we don't just say that the radius is from the center of the atom to the edge is because the electrons exist in a cloud, and so it's very difficult to say where the edge of the atom actually is. So instead, we take two atoms that are bonded together, in this case two hydrogen atoms. You measure the distance between the nucleus of one and the nucleus of the other, and we just say half of that distance is the radius. Now what you should have seen with the card activity is the atomic radius actually does something you don't expect as you move from left to right. So when you filled out what you thought the atomic radius was doing as you move from left to right, you should have actually seen that it decreases. And if you didn't see that, or if you said the opposite in the answers in your packet, take another look at the data that actually do decrease as we move from left to right. And also it is going to increase as we move down from top to bottom. So let's talk about why that is. And let's first of all just write down in our notes what those trends are. Now the left to right trend, because we call these horizontal rows on the periodic table, we call them periods. So we refer to the left to right trend across a row as the period trend. So underneath your definition of atomic radius, let's write down the period trend. So atomic radius, as you've already seen, decreases from left to right across a period. Now why is that? Well, if you think about it, what's happening here? Let's just highlight a couple of these atoms. Let's say we're talking about arsenic and selenium and bromine. These atoms are roughly the same size, but the question is, why would arsenic be larger than selenium, and why would selenium be larger than bromine? Because bromine actually has more electrons, and selenium has more electrons than arsenic. So we're actually going up in electrons as we move across that period. But the thing you have to keep in mind is the electrons that we're adding are just going into the outermost energy level. So for bromine, selenium, and argon, these guys all have 3 energy levels. So if this is my nucleus, first energy level with a couple of electrons, second energy level with some more electrons. I'm not going to worry about how many exactly I'm drawing. The third energy level, these guys actually have 4 energy levels. So third energy level would have a bunch of electrons, and it's even got some in the fourth energy level. Okay, so what determines the size of the atom is 2 things. How many energy levels do they have? And the 3 that I've highlighted, arsenic, selenium, and bromine, all have the same number of energy levels. So that doesn't really account for how they're different in size. What does change, though, is the number of protons in the nucleus. So arsenic has fewer protons than selenium. And so what happens is these protons are positive, and they pull these electrons in towards the center of the atom. And the more protons, the more positive protons you have, the smaller the atom becomes, because they're pulling the electrons, the negative electrons, in with more force if there's more of them. So of these 3 that I've highlighted, bromine would actually be the smallest, even though it has the most protons, because it has the most protons. because those 35 positive protons are pulling those negative electrons in with so much force. So that's why the atoms actually get smaller as we move from left to right across a period. Now they also get bigger though as we move down. So let me get rid of some of this. If I were to look at, let's say, fluorine, chlorine, bromine, iodine, acetine, what's happening is as we move down, yeah, there's more protons, but more importantly, there are more energy levels. So we're going from just 2 energy levels for fluorine to having 3 for chlorine, 4 for bromine, 5 for iodine, and 6 for acetine. So you're adding layers to the atom. So that becomes what we call our vertical trend is also known as the group trend. So radius increases down a group because energy levels are added. So there are more energy levels in these elements that are at the bottom of each group. Okay. Your next trend we're going to talk about is ionization energy. So ionization energy is a number that you saw in the activity, but you probably didn't know exactly what it meant. It just means the energy needed to remove an electron from an atom. So if you guys remember the alkali metals demo we did, so let's say we have a lithium atom. A lithium atom has a positive nucleus, and then it has just 2 energy levels of electrons. It has a couple of electrons in the first energy level, and then it just has 1 electron out here in the second energy level. So ionization energy is just describing how much energy is needed to pull that 1 electron away from the lithium atom. And what that has to do with is 2 things. How positive is the nucleus? So how many protons are there? And then how close is that nucleus to that electron that it's holding on to? So if you remember what we just talked about with atomic radius, everything to the left-hand side of the periodic table within a row are bigger atoms. And they also have fewer protons. So as I move from let's say across the second row of the periodic table, from neon to fluorine to oxygen, nitrogen, carbon, boron, beryllium, lithium, the nucleus is becoming less and less positive, and the atom is also becoming smaller and smaller. And so what that means is it becomes easier and easier across that row to remove an electron. Or the other way you could say it is, as you move from left to right, it's becoming harder and harder to remove an electron because the atom is getting smaller. For example, as we go from boron to carbon to nitrogen and so forth, the atoms are becoming smaller, and the number of protons in the nucleus is increasing, and those protons hold the electrons in. So ionization, we have a period trend, which says ionization energy increases from left to right, from L to R, because more protons are found in the nucleus. Holding the electrons in with more force. So if I compare, let's say, nitrogen right here with carbon, the nitrogen has 1 extra proton in the nucleus, and that 1 extra proton is going to pull those electrons and hold on to those electrons, keep them from being pulled away. That means it's going to take a lot of ionization energy to pull an electron away from a nitrogen atom. Now the group trend you should have found is that IE, ionization energy, decreases down a group. And the reason for that is because what happens to the size of the atom as we go down a group? Right, so you should have said that the atoms get bigger, and larger atoms lose electrons more easily. So the electrons are pulled away more easily. It takes less energy, less ionization energy. The last trend we have to talk about is electronegativity. So electronegativity is the pull that an atom exerts on shared electrons. So if you go back up to our picture of like the hydrogens sharing electrons and being bonded together, another example would be like a water molecule. And you guys talk about this a lot in biology. You've got positive nucleus of an oxygen atom, positive nucleus of two hydrogen atoms, and these electrons in between them in this kind of overlap area are being shared. Well, electronegativity is just describing how much pull does that oxygen nucleus exert on those shared electrons versus how much pull does the hydrogen nucleus exert. And so the electronegativity is just telling us which atom is pulling those shared electrons with more force. And the period trend for electronegativity is exactly like the one for ionization energy, and it's really for the same reason. More positive nucleus, smaller atom equals greater electronegativity. So the period trend is electronegativity, or En, increases from left to right. And then the group trend is that En decreases down a group. And again, I'm not writing the reasons because the reasons for the electronegativity trend are exactly like the reasons for the ionization energy trend. So if I go back up to my periodic table, get rid of some of this mess here. So if I wanted to compare, like, let's say oxygen to germanium, and say which one has a greater electronegativity, if they were both sharing electrons, in which direction would those electrons be pulled? And the answer is they'd be pulled a bit more towards the oxygen atom. And that's because the oxygen atom is much smaller, which means that its valence electrons, its outer electrons that are being shared, are a lot closer to that positive nucleus. So let's say this is my oxygen atom, and then I've got a great big germanium atom that it's bonded to. Here's the positive nucleus of the germanium atom. Here's the positive nucleus of the oxygen atom. These shared electrons are a lot closer to that smaller oxygen atom's positive nucleus. And so they're going to actually get pulled more toward the oxygen end of the bond. That's what electronegativity is telling us. To finish out our trends here, electronegativity and ionization energy are both follow the same trend here. They increase as we move to the right. They both do that. And they decrease as you move down the group. So they're the exact opposite of the atomic radius. So decrease and decrease. Okay? Decreases. There we go. So you can also look at this from a perspective of, which one is the biggest in terms of atomic radius on the periodic table, and which one's the smallest, and that'll help you remember what the trends are. The biggest atom in terms of radius on the whole periodic table would be francium, because it is the furthest one to the left and it is the furthest one to the bottom. The smallest atom on the whole periodic table would be helium. Now, if you talk about ionization energy, that would be flipped. So the greatest ionization energy on the whole periodic table is helium, because it's so small. And the francium, which is so large in terms of its size, has the least ionization energy. It's super easy to remove an electron from francium. And then the electronegativity is the same trend as ionization energy, the only difference being that because the noble gases don't share electrons, they're already stable, we just kind of forget about them when it comes to electronegativity. And so instead of helium being the greatest electronegativity, it's actually fluorine, which is the one that is, it's the one that's closest to helium that's not a noble gas.